In the spring of 1943, deep inside a secret laboratory in occupied Germany, a man sat hunched over a workbench with a scalpel so fine it could split a human hair lengthwise. Before him lay a single dead mosquito. Outside, the world was tearing itself apart. Cities burned. Armies clashed. Millions died. Yet this engineer, this obsessed, brilliant, half-mad German scientist, was about to unlock a secret hidden inside the body of an insect that would change the course of aerial warfare forever. He was about to discover that nature had already solved a problem that had killed thousands of Allied pilots. And the answer was glue. Not just any glue. A glue stronger than steel. His name was Hermann Zabel, though history has nearly forgotten him. He wasn't a household name like Wernher von Braun or Albert Speer. He didn't design rockets or build Atlantic walls. But what he did was perhaps more extraordinary, more bizarre, and ultimately more crucial than almost anyone realized at the time. Because Hermann Zabel was about to prove that the smallest creatures on Earth held the key to keeping the largest machines in the sky from falling apart. Let's go back to where this story really begins. It's the summer of 1942, and the skies over Europe are filled with metal monsters. British Lancaster bombers, American B-17 flying fortresses, German Messerschmitt fighters. These aircraft are technological marvels, the pinnacle of human engineering. But they have a fatal flaw. They're falling apart. Not from enemy fire, though that's certainly killing enough men. No, they're falling apart because of something far more insidious, something no one fully understood. The glue that held them together was failing. You see, these aircraft weren't built like cars. They weren't riveted metal through and through. Weight was everything in aviation. Every extra gram meant less fuel, less ammunition, less range. So engineers had turned to a revolutionary construction method. They were gluing parts together. Wooden components bonded to metal frames. Layers of plywood forming lightweight but strong structures. The British Mosquito bomber, one of the fastest aircraft of the war, was built almost entirely from wood and glue. It was a flying miracle except for one problem. The glue kept failing. Pilots reported terrifying incidents. Wings beginning to separate mid-flight. Tail sections showing cracks. Structural panels peeling away at high altitude. Some planes simply disintegrated in the air, their crews never knowing what hit them. The British traced dozens of crashes to adhesive failure. The problem was temperature. At 20,000 feet, where these bombers operated, temperatures could drop to 40 degrees below zero. The glues they were using, developed in warm laboratories, simply couldn't handle it. They became brittle. They cracked. They failed. And men died. The Germans faced the same problem, but they had an additional nightmare. They were running out of materials. By 1943, the Allied blockade had choked off supplies of critical metals. German engineers were forced to use more and more wood and composite materials in their aircraft. This meant more glue. But the glue they had was unreliable, inconsistent, and weakening under combat conditions. The Luftwaffe was losing planes not to superior Allied fighters, but to their own construction methods. This is where Hermann Zabel enters our story. He wasn't originally an aviation engineer. His background was in chemistry and biology, an unusual combination that his colleagues found eccentric. Before the war, he had studied natural adhesives, the ways that living things stick to each other and to surfaces. He was fascinated by spiderwebs, by the way barnacles cemented themselves to ships, by the incredible holding power of certain tree resins. His peers thought he was wasting his time. What practical application could such research possibly have? But when the adhesive crisis hit German aviation, someone remembered the strange chemist who studied how bugs stuck to things. Zabel was summoned to a meeting with Luftwaffe engineers in Berlin. They laid out the problem. They showed him reports of structural failures. They gave him samples of every glue being used in aircraft production. And they asked him a question: could nature do better? Zabel didn't answer immediately. He took the samples back to his laboratory, a cramped facility on the outskirts of Munich. For weeks he tested them under every condition he could simulate. Extreme cold, rapid temperature changes, high humidity, vibration, tension, compression. And he confirmed what the engineers already suspected. Every single adhesive they were using had fundamental weaknesses. The chemical bonds broke down under stress. The polymers became rigid and fractured in cold. The glues that worked at ground level became useless at altitude. But Zabel noticed something else. Something nobody had considered. When he examined the failure points under a microscope, he saw that the problem wasn't just the glue itself. It was the interface, the boundary between the adhesive and the material it was bonding. The glue wasn't penetrating deeply enough into the wood grain. It was sitting on the surface, creating a weak point where stress is concentrated. And this gave him an idea. In nature, adhesives don't just sit on surfaces. They integrate. They penetrate. They become part of the structure they're bonding. Spider silk doesn't just touch the web's anchor points, it merges with them at a molecular level. Barnacle cement actually becomes part of the rock it attaches to. The strongest adhesives in nature weren't separate from what they bonded. They were continuous with it. So Zabel began to study these natural adhesives in earnest. He collected spider silk from abandoned buildings. He scraped barnacles from the hulls of ships in Hamburg harbor. He gathered tree resins from forests. And then, one day in late 1942, he encountered something that would change everything. He was examining insects under his microscope, studying how their exoskeletons were put together, when he focused on a mosquito. The mosquito had been dead for some time, dried and preserved. But as Zabel adjusted his microscope, preparing to move on to another specimen, something caught his eye. The way the insect's wings attached to its body was remarkable. The joint was microscopically thin, yet it had to withstand incredible forces. A mosquito's wings beat hundreds of times per second. The stresses involved were enormous relative to the insect's size. Yet the connection never failed. Never wore out. Never came apart. Zabel became obsessed. How was this possible? What was holding these wings on? He needed to see inside to understand the structure. So he did something that his assistants thought was complete madness. He began to dissect the mosquito. With tools so delicate they had to be manipulated under magnification, he carefully, painstakingly, took the insect apart layer by microscopic layer. What he found astonished him. The wing joint wasn't held together by a single substance. It was a complex, layered structure. There were proteins arranged in crossing patterns creating a mesh. There were chitin fibers, the same material that made up the insect's exoskeleton, but oriented in specific directions to handle different types of stress. And there was a natural adhesive, a biological glue, but it wasn't sitting between the layers. It was interwoven with them, integrated at a molecular level. Zabel spent months analyzing this structure. He recruited chemists to help him identify the compounds involved. He had biologists examine other insects to see if the pattern repeated. And slowly he began to understand. Nature had solved the adhesive problem millions of years ago through evolution. The answer wasn't a better glue. It was a better way of using glue. The key was penetration and integration. The mosquito's adhesive didn't just bond surfaces together. It penetrated deep into the surrounding structure, creating a transition zone where glue and material gradually merged. This distributed stresses across a much larger area. There was no single weak point. No interface where everything could suddenly fail. The bond was as strong as the materials themselves. But could this be replicated in aircraft construction? Could you create an artificial adhesive that worked the same way? Zabel believed you could, but he needed to prove it. He began experimenting with modified formulations, adding compounds that would help the glue penetrate deeper into wood grain. He tried different application techniques, using heat and pressure to force adhesives into the microscopic structure of materials. He created layered bonds, applying multiple thin coats rather than one thick layer. The work was painstaking. Every experiment took weeks. He was working in wartime conditions with limited supplies and constant pressure to produce results. But gradually he made progress. He developed an adhesive system, not a single glue but a multi-step process, that created bonds far stronger than anything being used in aircraft production. In laboratory tests, his bonds were stronger than the wood itself. You couldn't pull them apart. The wood would fail first. But laboratory tests were one thing. Real aircraft were another. Zabel needed to convince the Luftwaffe to let him try his methods on actual planes. This was harder than it sounds. By 1943, Germany was losing the war. Resources were scarce. Trust in new, unproven technologies was low. Engineers were conservative. They'd rather stick with known problems than risk unknown ones. Zabel persisted. He created demonstration samples, bonding wood and metal with his new process and subjecting them to brutal stress tests. He froze them. He heated them. He vibrated them until conventional bonds failed. His samples held. Slowly, reluctantly, the Luftwaffe gave him permission for a trial. They would let him treat the wooden components of a single fighter aircraft using his methods. If it survived combat testing, they would consider broader application. The aircraft was a Focke-Wulf FW-190, a formidable fighter that was one of Germany's best. But it had a problem. Its tail section, which used wooden structural elements bonded to a metal frame, was showing stress cracks after extended high-altitude missions. It was the perfect test case. Zabel and his team carefully disassembled the tail section and rebuilt it using his adhesive process. They worked for 3 weeks, applying multiple layers, using precisely controlled temperatures and pressures, creating bonds that looked no different from the outside but were fundamentally different in structure. The aircraft was reassembled and sent to a test unit for evaluation. The pilot was a veteran named Klaus Brenner, a man who had survived 2 years of combat flying and had strong opinions about aircraft reliability. He was skeptical of the modifications. Another laboratory scientist who'd never been in combat telling him this would make his plane better. He'd heard it before. But Brenner's skepticism began to fade after his first high-altitude mission. The aircraft felt solid. There were no unusual vibrations, no creaking or flexing in the tail section. He pushed it harder, pulling tight turns, diving at maximum speed, subjecting the plane to stresses that would normally have revealed any structural weakness. Nothing. The tail held perfectly. Over the next 2 months, Brenner flew that aircraft on 17 combat missions. He engaged in dogfights. He was hit by anti-aircraft fire. He made emergency landings. The plane took damage, but the tail section showed no signs of adhesive failure. The bonds Zabel had created held through everything combat could throw at them. When the aircraft was finally brought back for inspection, engineers were amazed. The wooden components showed battle damage, but the glue joints were perfect. Stronger than the wood itself, just as Zabel had promised. News of the success spread quickly through German aviation circles. Here was a solution to one of their most persistent problems. Zabel was suddenly in demand. The Luftwaffe wanted his process applied to entire production lines. Engineers from different aircraft manufacturers came to Munich to learn his techniques. He was no longer the eccentric scientist studying dead insects. He was the man who had solved the glue problem. But there was a dark irony at the heart of this success. By the time Zabel's adhesive process was ready for large-scale implementation, Germany was already losing the war. It was late 1943, moving into 1944. The Allies had air superiority. German industry was being bombed around the clock. Supply chains were collapsing. Training new pilots was becoming impossible. No amount of better glue was going to change the strategic situation. Zabel himself seemed to understand this. His letters from this period, which survived the war, show a man grappling with the futility of his achievement. He had solved a genuine scientific problem. He had created something remarkable. But to what end? To help prolong a war that Germany couldn't win? To keep aircraft flying that would carry men to their deaths anyway? The Mosquito had given him its secret, but that secret was being used for destruction. Still, the work continued because that's what people did in wartime. They continued. Zabel trained technicians in his methods. He wrote detailed manuals. He supervised the conversion of production lines to use his adhesive process. Hundreds of German aircraft were built or retrofitted with his bonding system in 1944. And it worked. Structural failures due to adhesive breakdown dropped dramatically. Pilots reported aircraft that held together better under combat stress. In purely technical terms, it was a success. But here's where the story takes another turn. Because Zabel's work didn't die with the Third Reich. When the war ended in May 1945, Allied intelligence teams swept through Germany looking for advanced technology. They found jet engines. They found rocket designs. They found acoustic torpedoes and guided missiles. And buried in the files of the Luftwaffe's technical division, they found Hermann Zabel's research on natural adhesives and his methods for creating stronger bonds. American and British engineers were fascinated. They had been struggling with the same adhesive problems throughout the war. The British Mosquito, despite its success, had lost planes to glue failure. American bombers had experienced structural issues with bonded components. Here was a potential solution based on studying a mosquito of all things that seemed to work. Zabel himself was captured by American forces and interrogated, though interrogation is perhaps too strong a word. He was happy to explain his research. He had no loyalty to the Nazi regime, had never been a party member, and seemed almost relieved that the war was over. He shared everything he knew about natural adhesives and biomimetic engineering, a term that didn't even exist yet but that perfectly described what he had been doing. The Americans were particularly interested because they were already thinking about the next generation of aircraft. Jets. Supersonic planes. Spacecraft, though that seemed like pure fantasy at the time. These future aircraft would need even stronger, lighter materials. They would experience even more extreme temperatures and stresses. Zabel's approach of learning from nature, of understanding how biological systems solved engineering problems, seemed incredibly forward-thinking. So Zabel was brought to the United States as part of Operation Paperclip, the program that recruited German scientists and engineers. Not all of these men deserved to be rescued from the rubble of the Reich. Some had been deeply complicit in terrible crimes. But Zabel's record was clean. He had worked on glue, not weapons. He had studied insects, not conducted experiments on human beings. He was a scientist who had made a genuine discovery, regardless of who had been funding his laboratory. In America, Zabel continued his research, now working for the U.S. Air Force and eventually for NASA. His insights into natural adhesives influenced the development of epoxy resins, structural adhesives that became crucial to aerospace engineering. The bonding techniques he pioneered were used in aircraft, spacecraft, and eventually in countless civilian applications. Every time you see a modern aircraft with composite materials, every time you encounter a lightweight structure that's bonded rather than bolted or welded, you're seeing the legacy of Hermann Zabel's work. But very few people know his name. Very few people know that modern adhesive technology, the glues and epoxies that hold together so much of our technological world, were influenced by a German engineer who dissected a mosquito during World War II. History remembers the dramatic breakthroughs, the atomic bombs and radar systems and code-breaking computers. It forgets the small discoveries that turned out to be just as important in the long run. Zabel himself lived quietly in the United States until his death in 1978. He published papers on biomimetic engineering, a field he helped to found. He consulted for aerospace companies. He taught at universities. But he rarely talked about the war years, about the desperate search for better glue while the world burned around him. When he did discuss it, he always came back to the mosquito, to that moment when he looked through his microscope and saw how nature had solved a problem that human engineers couldn't. There's a broader lesson here beyond the specific story of glue and aircraft. It's about where innovation comes from. We tend to think of breakthroughs as coming from massive research programs, from teams of experts working in state-of-the-art facilities. And sometimes they do. But just as often they come from odd corners, from people pursuing strange questions, from someone wondering how a mosquito's wings stay attached. Zabel's discovery was only possible because he was willing to look in an unusual place, because he had the insight to connect biological systems to engineering problems. Nobody told him to dissect a mosquito. It wasn't part of any research directive. It was curiosity, pure and simple. The kind of curiosity that doesn't always lead anywhere useful but occasionally leads somewhere extraordinary. And there's something poignant about the fact that this discovery came in the middle of a war, when human ingenuity was focused so relentlessly on destruction. Zabel was trying to keep aircraft flying so they could bomb enemy cities and shoot down enemy planes. The immediate purpose of his work was violent. But the knowledge he gained, the understanding of how to create stronger bonds between materials, turned out to be useful for so much more. It helped build the modern world for better and worse. Today, researchers continue to study natural adhesives. Scientists examine gecko feet to understand how to create surfaces that stick without glue. They analyze muscle proteins to develop underwater adhesives. They study spider silk to create stronger fibers. This field of biomimicry, of learning from nature's solutions to engineering problems, is one of the most promising areas of research. And it all traces back, in part, to a mad German engineer with a microscope and a dead mosquito. So the next time you board an aircraft or use a product with composite materials, or encounter any of the countless applications of modern adhesive technology, remember Hermann Zabel. Remember that someone once looked at an insect and saw the future of engineering. Remember that the smallest creatures can teach us the greatest lessons. And remember that even in humanity's darkest hours, curiosity and insight can still produce something valuable, something that outlasts the conflict that gave it birth. The mosquito gave up its secret reluctantly, layer by microscopic layer. But once revealed, that secret changed the world. Not all at once. Not dramatically. But quietly, persistently, in ways that compound over time. That's how the best discoveries work. They don't explode. They integrate. Like glue that's stronger than steel, they become part of the structure of human knowledge, invisible but essential, holding things together in ways we take for granted until we stop to ask how it all works. And that was Hermann Zabel's gift. Not just a better adhesive, but a different way of thinking. A reminder to look at the world with wonder, to study the small things, to understand that nature has been solving engineering problems for millions of years, and maybe, just maybe, we should pay attention. The war ended. The aircraft fell from the skies or were scrapped. The urgent crisis that drove his research faded into history. But the insight remained. The glue held. And it holds still. But there's more to this story. Because what I haven't told you yet is how desperate things really were in those final years of the war, and how Zabel's discovery became entangled with some of the most secret projects of the Third Reich. Projects that would have seemed like pure science fiction if they hadn't been terrifyingly real. By early 1944, Germany was throwing everything it had at experimental aircraft designs. They knew conventional planes couldn't win the war anymore. Allied bombers were turning German cities to ash. The Luftwaffe was being overwhelmed. So German engineers were designing aircraft that pushed the boundaries of what seemed possible. Jet fighters that could outrun anything the Allies had. Rocket-powered interceptors. Flying wings. Bombers that could reach New York. Most of these designs would never leave the drawing board, but some did. And they all had one thing in common. They needed Zabel's glue. Consider the Messerschmitt Me-163 Comet. This was a rocket-powered interceptor, the only operational rocket fighter of World War II. It could climb to 30,000 feet in under 3 minutes. It could reach speeds of over 600 miles per hour, faster than any Allied aircraft could dream of achieving. But it was also a death trap. The rocket fuel was so corrosive it would dissolve human flesh on contact. The aircraft was so fast that pilots often blacked out from the G-forces. And the structure, built from lightweight wood and metal composites held together with adhesives, was constantly failing. Zabel was brought in to consult on the Me-163 program in the spring of 1944. He arrived at the test facility near Bad Zwischenen and immediately saw the problem. The engineers building these aircraft were using his adhesive process, but they were cutting corners. They were in a hurry, always in a hurry, because the war was being lost and desperate times bred desperate shortcuts. They weren't applying enough layers. They weren't controlling temperatures precisely enough. They were treating his carefully developed process like it was just another type of glue you could slap on and forget about. Zabel spent 2 months at that facility training technicians, supervising construction, ensuring that his methods were being followed exactly. He knew what was at stake. Not just the success of the aircraft program, though that mattered to the people he was working for, but the lives of the pilots who would fly these machines. Whatever else you can say about Zabel, and history has said many things, he cared about craftsmanship. He cared about doing things properly. And he couldn't stand the thought of pilots dying because someone had rushed through a bonding process. One of those pilots was a young man named Joseph Poes. He was 19 years old, had been flying for less than a year, and had been assigned to test a newly constructed Me-163. The aircraft had been built using Zabel's improved methods, but this was still one of the most dangerous aircraft ever created. On a cold morning in March 1944, Poes climbed into the cockpit, the rocket engine ignited with a sound like the world tearing apart, and he shot into the sky like a bullet. What happened next is recorded in the test flight reports that survived the war. Poes pushed the aircraft to its limits. He dove. He climbed. He pulled turns that would have ripped apart a conventional fighter. The G-forces were crushing. The airframe shook and screamed. But the structure held. The wooden wing spars, bonded to the metal fuselage with Zabel's adhesive system, didn't separate. Didn't crack. Didn't fail. When Poes landed, after the terrifying experience of a rocket engine flameout and a dead stick glide back to the airfield, the first thing he did after climbing out of the cockpit was find Zabel and shake his hand. But not all the pilots were so lucky. The Me-163 program killed more German pilots in accidents than it ever did Allied aircraft in combat. Some of those deaths were from structural failure, from adhesives that hadn't been applied correctly, from aircraft that came apart in mid-air. Zabel saw the reports. He saw the photographs of crash sites. And he carried that weight for the rest of his life. His discovery had been meant to save lives, to keep aircraft together, to prevent the very tragedies he was now witnessing. There was another project, even more secret than the Me-163, that required Zabel's expertise. This was the Horten Ho-229, a revolutionary flying wing design that looked like something from a future that hadn't happened yet. The Horten brothers, Walter and Reimar, were brilliant designers who believed that the flying wing configuration with no separate fuselage or tail was the future of aviation. They were probably right. Today's stealth bombers use the same basic design. But in 1944, building a flying wing presented enormous challenges. The aircraft had to be incredibly strong yet incredibly light. Every component had to carry load, had to be structural. There was no room for excess weight, no space for traditional construction methods. The entire aircraft was essentially a wing, built from a wooden frame covered with plywood and metal sheets, all bonded together with adhesives. If those bonds failed, the aircraft wouldn't just crash. It would disintegrate. The stresses on a flying wing are distributed completely differently from a conventional aircraft. One weak point, one failed joint, and the whole structure could come apart. Zabel was summoned to Göttingen, where the Horten brothers were working under intense pressure to get their flying wing operational. The Reich was collapsing. The Soviets were pushing from the east, the Americans and British from the west. There was talk that this aircraft, if it could be made to work, might turn the tide. It was nonsense, of course. One experimental aircraft couldn't change the strategic situation. But in early 1945, rational thinking was in short supply. The Horten brothers showed Zabel their design, and even he, who had seen dozens of experimental aircraft by this point, was impressed. The engineering was elegant, almost beautiful. But they were trying to build it too fast. They wanted to have a combat-ready aircraft in weeks when it should have taken months or years. Zabel told them this. He explained that his adhesive process couldn't be rushed, that it required time and precision. They told him he didn't understand the urgency. Germany was dying. They needed miracles, not careful craftsmanship. So they compromised. Zabel would oversee the bonding of the most critical structural components, the wing spars and the center section where all the stress is concentrated. The rest would be built using conventional methods as quickly as possible. It wasn't ideal, but it was the best he could do under the circumstances. He worked around the clock, sleeping in the factory, personally supervising every application of adhesive to the critical joints. His hands shook from exhaustion. His eyes burned from the chemical fumes. But he refused to delegate the important work. Too much depended on getting it right. The Ho-229 made its first flight on February 2, 1945. The pilot was a Luftwaffe test pilot named Erwin Ziller, a man with years of experience flying experimental aircraft. The flight was supposed to be brief, just a basic test to see if the aircraft was controllable. But Ziller was immediately impressed. The flying wing handled beautifully. It was fast, responsive, unlike anything he'd flown before. He pushed it harder than he was supposed to, climbing higher, turning tighter. The aircraft responded perfectly. The structure held. Zabel's bonds were doing their job. But on the second test flight, 2 weeks later, disaster struck. Ziller was testing the aircraft's stall characteristics when one of the experimental jet engines failed. Not because of any structural issue but because of a fuel system problem. The aircraft became uncontrollable. Ziller tried to bring it down, but the flying wing, with only one engine, couldn't maintain stable flight. He should have bailed out, but he tried to save the aircraft, tried to bring it back to the field. He almost made it. The Ho-229 crashed just short of the runway. Ziller was killed instantly. Zabel was there when it happened. He watched the aircraft come down, trailing smoke, watched it hit the ground and crumple. His immediate thought, before grief or horror could set in, was that the structure had failed. That his adhesives hadn't held. That he was responsible for another death. But when they examined the wreckage, they found that the structure was largely intact. The bonded joints had held through the crash. Ziller had died from the impact, not from structural failure. It was no comfort, but it was the truth. That was Zabel's last day working for the Luftwaffe. He walked away from the crash site, caught a train back to Munich and never returned. He'd had enough. Enough of building aircraft for a losing war. Enough of watching young men die. Enough of being complicit in the machinery of destruction, even if his role was just making better glue. The war was ending. Everyone knew it. Germany would be defeated within months. And Zabel wanted no part of whatever desperate last acts the regime was planning. He went into hiding, essentially. He continued his research in his laboratory, but he stopped reporting to his military supervisors. He stopped answering summons to meetings. As Germany collapsed into chaos in the spring of 1945, it was easy to disappear. The bureaucracy was falling apart. No one had time to track down an errant scientist who studied glue. Zabel used those final months of the war to document everything he'd learned, writing detailed technical reports not for the Reich but for whoever would come after. When American forces reached Munich in late April 1945, they found Zabel in his laboratory, surrounded by notes and specimens and microscopes. He was still studying natural adhesives, still trying to understand how biological systems created bonds stronger than anything human chemistry had achieved. The American soldiers who first encountered him thought he was crazy. Here was Germany falling to pieces, the war clearly over, and this man was peering at insects under a microscope like nothing else mattered. But the intelligence officers who came later understood immediately that they'd found something valuable. Not weapons. Not rockets or jets or secret bombs. But knowledge. Pure, applicable, transformative knowledge about materials science and biomimetic engineering. They packaged up Zabel's research, filled an entire truck with his notes and specimens, and made arrangements to transport him to the United States. The journey was surreal. Zabel traveled by military convoy through the ruins of Germany, seeing firsthand the devastation that war had brought. Cities reduced to rubble. Refugees clogging the roads. The infrastructure of an entire nation destroyed. And he thought about his glue, about how he'd worked so hard to keep aircraft flying, to extend the war by even a few days or weeks. Had it been worth it? Had his discovery, pulled from the body of a mosquito, made the world better or worse? He never really answered that question, not to anyone's satisfaction, probably not to his own. But he did something with it. When he arrived in America, when he began working for the Air Force and later for NASA, he made a conscious decision. He would use what he'd learned not for destruction but for exploration. Not to build bombers but to build spacecraft. Not to kill but to discover. In the 1950s, Zabel became part of the team developing adhesives for the early space program. The challenges were similar to what he'd faced during the war but even more extreme. Spacecraft had to withstand the vacuum of space, cosmic radiation, temperature swings of hundreds of degrees. Traditional mechanical fasteners added weight and created stress points. Adhesives were essential but they had to be perfect. A single bond failure in space could be catastrophic. Zabel brought everything he'd learned from the Mosquito to this new challenge. The principle of integration, of creating bonds that merged with the materials they connected, became fundamental to aerospace adhesive technology. He worked on the Mercury program, the Gemini program, and eventually the Apollo program. Every spacecraft that carried American astronauts into space used adhesive systems that incorporated his insights. There's a beautiful irony here. The research that began with trying to keep Luftwaffe fighters in the air ended up helping put human beings on the moon. The knowledge pulled from a dead mosquito in Nazi Germany became part of humanity's greatest peaceful achievement. Zabel saw this clearly. In his later writings, he often reflected on the strange path his career had taken, from war to space, from destruction to exploration. But he never forgot the cost. He never forgot the pilots who had died testing aircraft he'd worked on. He never forgot that his discoveries had been made in the service of a regime that committed unspeakable atrocities. This created a complicated legacy. Was Zabel a hero? A villain? Neither? Both? History struggles with such questions. We want our stories to be simple, our heroes pure, our villains irredeemable. But real life rarely cooperates. What we can say for certain is that Zabel made a genuine scientific discovery. He identified a principle of nature that had applications far beyond what he initially imagined. And he spent the second half of his life trying to use that discovery for something better than war. Whether that redeems his work for the Luftwaffe is a question everyone has to answer for themselves. Let's talk about some of the other scientists who were part of Zabel's story because he didn't work in isolation. There was a whole community of German researchers during the war studying biomimicry before that word existed. They were looking at how birds flew, how fish swam, how insects built their colonies. Some of this research was pure scientific curiosity. Some was driven by military necessity. And some was motivated by the simple fact that studying nature was a way to remain human in an increasingly inhumane world. One of Zabel's closest colleagues was a woman named Margret Kirchhoff. She was a biologist who specialized in insect physiology, and she was the one who first suggested to Zabel that he look at wing joints as a model for adhesive connections. Kirchhoff's story is remarkable in its own right. She was a Jewish scientist who had managed to continue working through the early years of the Nazi regime by hiding her heritage. But by 1943 she was in constant danger. Zabel helped protect her, using his connections with the Luftwaffe to keep her classified as essential to the war effort and therefore protected from deportation. It was a dangerous game. If the Gestapo had discovered what Zabel was doing, both he and Kirchhoff would have been arrested. But he did it anyway and Kirchhoff survived the war because of it. After 1945, she emigrated to Israel, where she continued her research on insect biology and remained in correspondence with Zabel for the rest of her life. Their letters, preserved in archives in Tel Aviv and Washington, show a friendship forged in the worst of times and maintained through shared scientific passion. Kirchhoff was the one who taught Zabel to really see insects, not just as specimens but as highly evolved machines that had solved engineering problems through millions of years of natural selection. She showed him how to think about biological structures in mechanical terms, how to ask the right questions. Why does this joint work? What forces is it resisting? How does it distribute stress? These questions, simple but profound, became the foundation of Zabel's approach. There was also Friedrich Albrecht, a chemist who worked with Zabel on synthesizing the adhesive formulations. Albrecht was a different type entirely, a pure pragmatist who cared nothing for the politics of the regime or the ethics of the work. He was interested in solving chemical problems, period. He and Zabel often clashed. Albrecht wanted to cut corners to find faster, easier solutions. Zabel insisted on precision and patience. But they needed each other. Zabel understood the biological principles but wasn't sophisticated enough in chemistry to create the compounds he envisioned. Albrecht could synthesize almost anything but needed Zabel to tell him what to make. After the war, Albrecht ended up in the Soviet Union, also recruited as part of the post-war scramble for German scientific talent. He worked on similar problems for the Soviet aerospace program, developing adhesives for MiG fighters and eventually for the Soviet space program. It's one of the strange parallels of the Cold War that both superpowers were using adhesive technology derived from the same wartime research, developed by colleagues who ended up on opposite sides of the Iron Curtain. The Soviets, it turns out, had their own version of Zabel. His name was Alexei Mikhailovich Isiev, and he had independently come to similar conclusions about natural adhesives during the siege of Leningrad. Trapped in the city with resources scarce and aircraft falling apart, Isiev had started looking at how trees bonded bark to wood, how natural resins worked. He never got as far as Zabel did, never had the laboratory facilities or the time, but his notes show that he was thinking along the same lines. After the war, when Soviet intelligence got hold of Zabel's research, Isiev immediately recognized the value and helped adapt the techniques for Soviet use. This raises an interesting question about scientific discovery. How much of it is individual genius and how much is simply being in the right place at the right time, asking questions that the moment demands? Would someone else have dissected a mosquito and discovered the same principles if Zabel hadn't? Probably, eventually. Science tends toward certain conclusions. Different people in different places often make similar discoveries independently because they're all looking at the same reality, all trying to solve similar problems. But that doesn't diminish Zabel's achievement. He was the one who did it, who made the connections, who developed the practical applications. Back in America, Zabel's work caught the attention of some of the biggest names in aerospace. Howard Hughes, the eccentric billionaire and aviation pioneer, met with Zabel in 1947 to discuss adhesives for his massive H-4 Hercules flying boat, the famous Spruce Goose. The aircraft was built almost entirely of wood because of wartime metal restrictions, and Hughes was obsessed with making the strongest, lightest structure possible. He and Zabel spent hours discussing bonding techniques, natural resins, the properties of different wood species. The Spruce Goose flew only once, a brief hop across Long Beach Harbor in November 1947, but it demonstrated that massive wooden aircraft were structurally viable. Much of that was due to the adhesive technology, including techniques derived from Zabel's wartime research. Hughes was so impressed that he hired Zabel as a consultant for Hughes Aircraft, where he worked on adhesives for jet fighters and eventually for satellites. Then there was Kelly Johnson, the legendary designer at Lockheed Skunk Works. Johnson was developing the U-2 spy plane in the mid-1950s, an aircraft that had to fly higher than anything before it, where temperatures and pressures were more extreme than any aircraft had ever experienced. The U-2 needed to be incredibly light, which meant extensive use of composite materials and adhesive bonding. Johnson brought Zabel in to consult on the bonding processes, and Zabel's techniques became part of the U-2's construction. Years later, when Johnson was designing the State Route 71 Blackbird, an aircraft that would fly at 3 times the speed of sound and experience temperatures that would melt conventional adhesives, he again consulted with Zabel. By this point, Zabel was in his 60s and officially retired, but he couldn't resist the challenge. The State Route 71 required completely new adhesive systems that could withstand temperatures of over 500 degrees Fahrenheit while maintaining structural integrity. Zabel helped develop those systems, bringing his decades of experience and his fundamental understanding of how bonds work at a molecular level. The State Route 71 first flew in 1964, and it remained in service until 1998, a testament to how well it was built. Those adhesive bonds, designed in part by a man who started by dissecting a mosquito, held together through thousands of flights at the edge of space. Pilots who flew the Blackbird talk about watching the aircraft change shape in flight, the metal expanding from heat, everything flexing and moving, yet the structure never failed. That's the legacy of good adhesive engineering. But perhaps Zabel's most important contribution came not from any specific aircraft or spacecraft but from how he changed the way engineers thought about materials. Before Zabel, adhesives were often an afterthought, something you used when you couldn't use bolts or welds. After Zabel, adhesive bonding became a primary structural technique, something you designed for from the beginning. Modern aircraft like the Boeing 787 or the Airbus A350 use thousands of adhesive bonds as primary structure. The wings, the fuselage, the control surfaces all depend on adhesives working perfectly under extreme conditions. This shift in thinking, this elevation of adhesive bonding from a secondary technique to a primary one, can be traced directly back to Zabel's work. He proved that adhesives could be stronger than traditional fasteners if they were designed and applied correctly. He showed that bonding could reduce weight, improve aerodynamics, and create structures that were actually more reliable than mechanically fastened ones. And he did it by studying a mosquito. There's something profound about that chain of causation. A tiny insect, product of millions of years of evolution, contains within its body a solution to engineering problems that humans struggled with for decades. Zabel had the insight to look, the patience to understand, and the skill to apply what he learned. That's the essence of biomimicry, and it's become one of the most productive areas of modern engineering. Today, researchers study butterfly wings to create better solar panels. They study termite mounds to design more efficient air conditioning systems. They study shark skin to reduce drag on ships and aircraft. All of this follows the pattern that Zabel helped establish. Nature has already solved most of the engineering problems we face. We just need to learn to read the solutions. But there's a darker side to this story that we can't ignore. All of Zabel's wartime work, all of his insights and discoveries, were made in service of the Nazi war machine. The aircraft he helped keep flying were bombing cities and shooting down Allied planes. The knowledge he generated was used to kill people. Does the fact that this knowledge later found peaceful applications absolve that original sin? It's not a simple question. Some historians argue that scientists like Zabel were simply doing their jobs, that they were apolitical actors caught up in events beyond their control. Others argue that this is exactly the kind of rationalization that allows atrocities to happen, that there's no such thing as apolitical science when you're working for a genocidal regime. Both positions have merit. The truth is probably somewhere in between, in the messy, complicated reality where people make imperfect choices under impossible circumstances. What we know for certain is that Zabel wrestled with these questions himself. His post-war writings show a man deeply troubled by what his work had been used for, even as he remained proud of the scientific achievements themselves. He seemed to believe that knowledge itself was neutral, that it was the application that mattered. A better adhesive could hold together a bomber or a spacecraft. The glue didn't care. But the person who made the glue, who chose to work for the Luftwaffe or for NASA, that person had to care. And Zabel did care, eventually. He spent the second half of his life trying to use his knowledge for exploration rather than destruction, for building rather than bombing. Whether that's enough, whether that balances the scales, is something each person has to judge for themselves. History is full of such uncomfortable compromises, brilliant people who did remarkable work in service of terrible causes, and we struggle to know how to remember them. What's undeniable is the lasting impact of the discovery itself. The principle that Zabel pulled from the mosquito's wing joint, that successful bonds integrate rather than just connect, that they merge with the materials they join, has influenced everything from automotive manufacturing to medical devices. Your smartphone is held together with structural adhesives designed according to principles Zabel helped establish. The artificial heart valve that might one day save your life uses bonding techniques descended from his work. The wind turbines generating clean energy use adhesives that follow the same fundamental principles. So the mosquito's gift, given up reluctantly to a German scientist in a wartime laboratory, continues to shape the world in ways large and small. It's a reminder that knowledge, once discovered, escapes the circumstances of its creation. It becomes part of humanity's inheritance, available to anyone who can understand and apply it. For good or ill, for war or peace, for destruction or creation, the knowledge persists. And perhaps that's the real lesson of Hermann Zabel's story. Not that we should celebrate him as a hero or condemn him as a villain, but that we should recognize the power and the burden of scientific knowledge. Every discovery is a double-edged sword. Every breakthrough can be used to help or to harm. The mosquito couldn't have known that when it died on Zabel's workbench. Evolution had given it strong wing joints so it could survive and reproduce, not so a human engineer could learn its secrets. But those secrets were learned anyway and they changed the world. That's how science works. That's how knowledge accumulates and compounds and shapes the future in ways nobody can fully predict. Zabel died in 1978 in a small house in Pasadena, California, surrounded by books and microscopes and specimens he'd been studying for decades. He was 81 years old, had lived through 2 world wars, had seen humanity go from propeller aircraft to moon landings, had been part of one of the most remarkable technological transformations in history. His obituary in the local paper was brief, mentioning his work for NASA but not his wartime research. Most of his neighbors had no idea what he'd done, what he'd discovered, what role he'd played in the development of modern aerospace. But in the aerospace community, his death was noted with respect. Engineers who had worked with him shared stories. How meticulous he'd been, how insistent on precision, how he'd refused to accept anything less than perfection. How he'd approach every problem by first asking what nature had already figured out. How he'd spend hours explaining the molecular structure of chitin or the properties of natural resins, his eyes lighting up with the same enthusiasm he'd had as a young researcher in Munich. His papers and specimens were donated to the Smithsonian, where they sit today in climate-controlled storage, available to researchers but rarely accessed. Most people studying modern adhesives have never heard of Hermann Zabel. They use techniques and follow principles that trace back to his work without knowing the origin. That's how science progresses. We stand on the shoulders of giants, but we often don't know their names. Except now you know. You know about the mad German engineer who dissected a mosquito in the middle of World War II and found that glue could be stronger than steel. You know about the desperate search for better adhesives while the world burned. You know about the pilots who died and the pilots who lived because of better bonds. You know about the journey from Luftwaffe laboratory to NASA cleanroom, from war to peace, from destruction to exploration. And maybe, just maybe, you'll look at the world a little differently now. Maybe when you see an insect, you'll wonder what engineering secrets it might contain. Maybe when you board an aircraft, you'll think about all the invisible bonds holding it together, the accumulated knowledge from decades of research stretching back to a man and his microscope. Maybe you'll appreciate that the smallest creatures have taught us some of the greatest lessons, if only we're willing to look and patient enough to understand. The mosquito is gone. Zabel is gone. But the knowledge remains. The glue still holds. And somewhere, right now, a researcher is looking at something small and wondering what secrets it might reveal, what problems it might solve, what impossible thing it might make possible. That's the real legacy. Not the aircraft or the spacecraft or the countless applications of better adhesives. But the idea that nature is the greatest engineer, and all we have to do is learn to read the blueprints written in the bodies of living things. That was Hermann Zabel's greatest discovery. Not a better glue, but a better way of seeing the world. And that, more than anything, is what holds us together, what bonds the past to the future, what connects the smallest moments of insight to the largest transformations of civilization. Like the mosquito's wing joint, like the adhesive that penetrates and integrates and becomes inseparable from what it joins, the best ideas become part of us. Invisible but essential. Strong enough to hold the world together. Stronger than steel.